Hello everyone and welcome back. Today I will be talking about um, tunneling effect, which is a phenomenon that happens in quantum mechanics, okay, which is paradigmatic if you want, and where something very strange happens. Let's try to set the scene and then to understand where does this effect come from. So first of all, we can draw a classical scenario where we have a ground and we dig a hole in the ground, okay, and then we put a ball, an object of mass m at the bottom of the hole in the ground. Okay, now for all we know, if the velocity of the object is zero, so v initial is zero, we know that F equal ma, which is the classical equation of motions, will lead to a very simple situation. Mg is the force acting, the gravity pull towards the center of Earth, and then there is a reaction on the ground, which is the normal force that is basically given by the elasticity of the ground. And since the particle is resting at the bottom, I mean, it's there, it's not moving, it's not digging a hole because it's too heavy, these two forces are balancing, so N equal mg. So the total force, which is the sum of the two, is zero. If the total force is zero, zero is also equal to mass times acceleration, because F equal ma, as we know from here, right? So these two are zero. This leads to the simple fact that the velocity is equal to initial velocity, which is zero because we know that the initial velocity is zero, and the position is the initial position, which is h in this case, because I want to put, for example, oh no, actually, let's say minus h, because I put our potential like this. This is x, and this is v, and this is minus h, this distance here, this is zero. Okay, so very simple. There is nothing new to it. We know that if the ball has no kinetic energy, there is no force, the ball will stay there. Now, of course, there is the other case that we can think of, that for some reason a force applied to the ball has given some kinetic component to the mass, some velocity, initial velocity, and we know that initial velocity, the kinetic energy plus, in this case, minus mgh, is equal to can be equal to the um, energy in this position here. Okay, so we have the initial position here at t0 and the final position here at t1, and we know that this is possible to solve because the potential energy here is zero because we are at the ground level, so we have only final velocity and final velocity. And if we equate these two with these two sides, we will find the final velocity of the particle here. And of course, it's not possible if the initial velocity is zero. Okay, we know that, so we need to give some force, some velocity to the particle to escape the potential trap the hole that we dig for the ball. This is very simple. We know that. Now, what I want to show you, maybe skipping some details, is what happens when instead of F equal ma, we use the equation, the usual equation, which is derivative over time of psi is equal h psi, the Schrödinger equation. But we want to solve the Schrödinger equation for a particular case, the stationary case, when the derivative of time is constant. So we want to solve the equation. This is a standard trick that is used in quantum mechanics. You solve for the constant equation, and then you can sum up the solution for the time varying equation. But to make our life easy, we solve the equation, the stationary equation, which is the one where the derivative of time is a constant, which is the energy. So the eigenfunctions, the eigensolution, if you want. And of course the Hamiltonian is 1 mp, v square plus the potential. And actually it's minus the potential. Okay. No, sorry, the plus the potential. And this can be written in other terms, 1 over 2m p square plus the potential. Okay, where p, we know that p is equal m times v. Why p? Because we already know that the operator, the p, is actually minus ih, the derivative over x. We know that from previous videos, so it's a partial derivative. So this equation, if you do the substitution, leads to the equation, the differential equation that we know of, or we can check, which is minus h to m second derivative over space psi minus v minus e psi is equal to 0, where I explicit the Hamiltonian in terms of the kinetic energy and the potential energy. Okay, now we want to do an extra step. We want again to simplify our lives. We cancel the potential in that way, and we dig a hole which is square. Why? Because the math is easier. We don't have to deal with the intricacy of the analytic solution, and we can do some approximation. Okay, in this case there is no, let's say there is still a pull of gravity, but well, let's say it's a different scenario. It's an electron around the nucleus of a proton. So the potential should be Coulombian, but we maybe with some approximation we can make it square in some configurations. It doesn't matter. We can engineer the potential in such a way that we make it square. I just want to show you where the point of the tunneling comes from. Okay, naturally we have three areas. One, area A, area B, which is this one, and area C, which is the one in the middle. And in these three areas, the equations are different, because in the one in C, we have this equation, but in B and A, there is no potential, so there is only plus E psi is equal to 0. Okay, and this is a minus. And this is quite of a big difference, because we can And one important thing that we need to remember is that the solution needs to be continuous between the A, B, and C. So if you draw a line, if you draw a solution, suppose a squiggly line, it needs to cross the barrier. Well, it needs to be, well, that's the point. It needs to continuous over the barrier for some reason, because this equation needs to be solved in all these areas, and needs to be the same at the intersection point. Okay. Okay. So I'm giving you already the idea of why there would be tunneling. The fact that the solution must be continuous at the boundaries tells us that if we have a solution inside the well, suppose we have a solution inside the well, which is like this, it cannot stop there, because otherwise this part is not satisfied. We need to satisfy also this part of the equation in order to have a full solution. And we can simplify this equation by removing the constant. The partial derivative is not important because it's just one variable, so we can do derivative over x square, simple derivative, and then we have this constant is k minus k, and this constant is plus k1 and plus k2. And there is a sign, there is a difference in the sign, okay? And this is quite important, because in one case it will lead to yes, this sign here that depends on the value of the constant, and the constant k1 is v minus e. So even when the energy is 0, so the least amount, so there is no kinetic energy if you want, there is only potential energy, this will have a solution, which is, this is an harmonic equation, as you can see. So the solution will lead to solution of the kind sinus of k1t h. There is all the I simplify the constant but I put the mass and the h bar inside the constant. But as you can see, this is a harmonic solution. If you want, it's like this. If you want, it's like E equal minus this. And this is a harmonic solution. We have solution, oscillatory solution, like this one, the one that I draw. While the one below, where kappa 2 is positive because it's the energy, there is no potential, is actually an exponential solution. So this one will lead to something like e to the minus kappa 2x. So and this is an x, not a t. X, because it's in space. Okay, so we have to make sure that these two, and there is a constant here and a constant here, whatever, it doesn't matter. The amplitude needs to, and these two equation needs to match at this boundary condition here, a minus a. Sorry, a and minus a. So you can solve the equation, you can find the condition for which a and b, for which this is satisfied, and you will see that there will be an exponential decay at both sides, because this happens in region A and in region B, where you flip the sign. So you will get two exponentials. Okay, and this is very important. So just by the fact that there is no potential, there is a change of sign in this equation. This will stay the same. There is a change of sign in this equation, if you want, like this. And this will lead to two different kind of solution. We know that. One is an auxiliary oscillatory solution and the other is a decaying solution. So there are two different solutions. And this is for the ground state, even when the energy is zero. This is the least amount of energy that you can, the particle at rest, if you want. So it's exactly this, the analogous situation where we were before, where F equal ma was equal to 0. In that situation, the particle would be stuck there. But in this case, as you can see, there is a chance, which is this area here, because we know that the amplitude, the psi square, is the probability of finding the particle in that area. So this area here, the integral of this area here, is the probability of finding the particle outside the box, even if there is no energy. And this is very natural coming from the Schrödinger equation in a simplified case, yes, but just purely by following the math. And the reason, as I said, the reason behind this is because the solution needs to exist in every part of the space, because that's the condition for the Schrödinger equation to be satisfied. Okay, so just to recap, I want to erase this to equation. We know that a change of sign in the harmonic equation can lead to a different solution. One is oscillatory and the other is exponential, and we know that, and it's basically this fact here: a square x is different from minus a square x. Those two leads to different solution. One is oscillatory and the other is exponential. This minus comes from the fact that in one case the constant is v minus a divided by m to m divided by h, and in the other case is just e to m divided by h. So these two constant k1 and k2 will have a different sign in the equation of motion. Okay, so with this difference of sign, we have different oscillate with different behavior, but they need to be the same value at the junction between the two, between the barrier and the outside world, because this is a continuous equation. There is no reason why there would be a jump there. And this leads naturally to the fact that the particle has a chance to escape the potential energy. Escape the potential well, if you want, with some small probability, but it exists. And this is called tunneling effect. Okay, so I hope I capture your attention, and yes, follow for more, and I will maybe post another video with some animation for this tunneling effect. But for now, I will see you next time. Thanks a lot. Bye.